Welcome, everybody. We are extremely happy to have John Baez from UC Riverside, who will talk about compositional modeling with decorated Cospans. Please, John, to you.
Thank you very much. It's great to be invited to speak here. So this is some work that I've done with a team of people. So Xiaoyan Li and Nathaniel Osgood are at the University of Saskatchewan in Canada, and they are epidemiologists primarily and computer modelers of epidemiology. Sophie Libkind at the Topos Institute. Programming with category theory, and it's the combination of all these ideas which led to the work here. So let me start out a little bit historically. So back in 2012, I asked my grad student, Brendan Fong, he was then my grad student, to create and study a category where the morphisms were open electrical circuits. So here in this example, I'm just showing an electrical circuit with some resistors on wires, and it's open, meaning that there's some wires dangling out at the left and right. And so you could imagine building larger electrical circuits out of these open pieces by sticking the outputs of one circuit onto the inputs of another circuit. And of course, that is how we indeed build complicated electrical circuits, by gluing together smaller pieces. But that form of composition is exactly the type of thing you'd expect when you're composing morphisms in a category. So I thought this should be really interesting. All the electrical appliances we have in our homes, you can think of them as morphisms in a category, and when we hook them up to each other, we're composing morphisms. So there should be some very nice mathematical theory behind this that's implicit in what electrical engineers are doing. And so he thought about this for a while, and then he wrote his thesis and invented a general theory, which is called the theory of decorated Cospans, to solve this problem, but also to solve lots of other problems, because electrical circuits are just an example of the different kind of diagrams that we use. I mean, electrical circuit diagrams are an example of the diagrams we use to describe the complicated apparatus of modern life. And his thesis is called The Algebra of Open and Interconnected Systems. And if you get the slides of the talk, you can click on that blue stuff and see the thesis. So he developed this general theory, and by now decorated Cospans have been used to study lots of different kinds of open systems. So I'll start out by talking about open graphs, which is sort of the mathematically simplest example, where you just have a graph as your type of network or open network that you're sticking together. But there are things called Petri nets that are widely used in computer science, and you can study them as open systems. There are open Petri nets where the so-called transitions of the Petri nets have rates, and those are more or less the same thing as what are called chemical reaction networks, where you describe how a bunch of different chemicals can react at various rates and turn into other chemicals. There are open electrical circuits. There are open Markov processes that have been studied. There are open dynamical systems, which I will talk about a little bit, and open StockFlow diagrams, which I will also explain and talk about. So each of these blue things is a link to a paper which has used decorated Cospans to study some type of open system. But I want to start out with an example to make it more concrete, and I'll do the simplest one that I said was open graphs. So here's a picture of an open graph. So what you see in the middle here is a graph. What makes it open is that we have two finite sets, A and B, and we have maps from those finite sets to the set of nodes of the graph. So the nodes N1 through N4 are these dots here, and we have functions from A and B to the set of nodes. You'll notice that I haven't labeled the edges of the graph, and we'll see why later. Also, you'll notice that I'm using graphs of the sort that category theorists like, or other people like. Sometimes they call them quivers. So they're graphs where they are directed, the edges have arrows on them, and they allow multiple edges from one node to another. And they also allow self loops, an edge from a vertex or node to itself, although I haven't drawn one of those here. So they're open graphs, and the main thing you can do with open graphs that you can't do with plain old graphs is that you can compose them. So here I have an open graph, which I'll call, say, from A to B. It's from the set A to the set B. And here I have an open graph from B to C. And the way we compose them is just sort of the obvious way. We stick them together. So in other words, whenever there's a point in the set B that's mapped to a node in our first open graph and mapped to some other node in our second open graph, we identify those two nodes. So we identify M4 and N1, and we get this node here, which I'll call X. Whoops. And similarly, we identify M5 and N2, and I'm calling that Y. So it's a very simple idea. We're just sticking together two open graphs to get a new one. And the idea is we want to think of these open graphs as morphisms in a category, and we want to think of composition of these morphisms as this process of gluing together open graphs. And the reason why we want to think of it as a category is because basically that's what it is. The composition is associative. Well, we have to be a little bit careful here. When we stick together these two graphs, open graphs, notice I had to make up some kind of name for these nodes that have been formed by gluing together a node of the first open graph and a node of the second. So here I just arbitrarily call them X and Y. Those choices are completely arbitrary. So if you think about it, you do have the possibility that when you check out the associative law, the two sides of the associative law will give you two different open graphs that aren't exactly the same because you have accidentally picked some different names for the nodes that appear when you glue together some open graphs. So in other words, you may not get exactly the same open graph when you compose three open graphs in a row, either composing the first two and then the third, or the first and then the second two. But it's associative up to isomorphism, that is, up to relabeling of these nodes. So what we should really do is work with isomorphism classes of open graphs to get a composition that's associative. And then those equivalence classes of open graphs will be the morphisms of a category. That's a little bit of a technical detail, but us category theorists are very fond of these little details, getting everything exactly right. So the point is you can get a category that way, and I'll explain in more technical detail now how we're going to get that category, but I'm going to describe it in a very general way. I'll describe the general procedure called decorated Cospans for building categories of this general sort, and the same procedure works for all the other examples that I listed, and lots more as well. So here we'll go over what I just said in a bit more detail. So given a finite set N, which I'll call like a set of nodes, I'll define this concept of a graph on N. So it's a graph with N as its set of nodes. So in other words, what it is it's a finite set E of edges, and then two different functions called source and target that assign to each edge its source node and its target node. So this type of graph is, as I mentioned before, called if you could call it like a directed multi-graph with self-loops, but that's a horrible name. You could call it a quiver. That's another name. Now, it's possible for two graphs with the same set of nodes n to be isomorphic, we could have one with set of edges E, and we could have another one with set of edges E prime. We'll say that they're isomorphic if there's a bijection F here from E to E prime that makes these two diagrams commute. So what this means is that the only difference between these two graphs is the names of the edges, and F, this bijection, is just the thing that converts the names we had over here to the names we had over here. So an open graph, now I'll define more rigorously, it's a cospan of finite sets. Cospan is a perhaps scary name if you've never heard it, but it just means, in this particular case, a cospan of finite sets just means three different finite sets and two functions between them, pointing from the two on the outside to the one in the middle there. That's what a cospan is. So in other words, a cospan is just the thing you see before you here, but no secret extra stuff you're supposed to know. I and O are just our arbitrary functions. And an isomorphism class of graphs on the set N. So here's an example of an open graph. So A and B are input and output finite sets. N is the set of nodes. Apparently I can't count N1, N2, N3, and N4, it's supposed to say. And then we have an isomorphism class of graphs on this set N1, N2, N3, N4. It's an isomorphism class of graphs. So in other words, the edges do not have specific names anymore, because if we had a specific graph, the edges would have some names, but if you just have an isomorphism class of graphs, the names have been washed out, so to speak. So that's why these edges don't have names. Okay, now for each finite set N, there's a set F of N of isomorphism classes of graphs on that set N. And the idea of decorated cospans is that we abstract out the properties of this example to build a general procedure for dealing with things like open graphs, but also open electrical circuits, open StockFlow diagrams, all sorts of other open things. And so what Brendan Fong did is he abstracted out what about this set F of N we really need to make the whole game work. And it turns out that what we need is that this assignment, F, needs to give us what's called a symmetric lax monoidal functor. Now, various of you may have different amounts of knowledge of category theory. So I think my attitude will be to, instead of giving huge amounts of detail, to give just the salient amount of detail and hope that works even for the people who don't know what all the buzzwords mean. So here what we're saying, for starters, is that for each finite set N, we are getting a set of all, well, in this case, a set of all isomorphism classes of graphs on N. There's properties of this F here, which most importantly that it's a functor, but also other things. And one crucial thing is that it's lax monoidal. And so what does that mean? It means that we have these maps of this sort. So from F of M times F of N to F of M plus N. But what does that map do? Well, what it does is something very simple. If I have an element of F of M, it's an isomorphism class of graphs on some set M. So here I've drawn an isomorphism class of graphs on the set M1 through M4. And here's similarly an element of F of N. And so if I have these two guys, I can just imagine setting them side by side. Think of this whole big picture as a graph, or more precisely an isomorphism class of graphs. And you'll notice its set of nodes is the disjoint union of the sets M and N. So that's what M plus N means here. So this guy here, this whole big picture, is an element of F of M plus N. So I'm just asserting that, right, that I can combine a graph on isomorphism class of graphs on the set M with one on the set N to get one on the set M plus N. And so we get these maps, DMN. And you'll notice that this map is not a bijection. There are also lots of other graphs on the set M plus N that aren't of this form where there's like one part over here and one part over here. So these maps are not bijections. And that's where the word lax is coming in. There are other situations where you have isomorphisms of this sort, but here that's not what we have. We just have a map. I should emphasize that people should feel free to ask questions. I may not manage to keep a careful eye on the chat, but I'll try. But people should, I guess, also feel free to interrupt, or maybe the leaders of the seminar can interrupt me if they see questions appearing. So, okay, so what I'm claiming is that this structure, the symmetric lax monoidal functor, is the key to getting a category of open, where the morphisms are open graphs. So let's see how that works, but we'll do it generally. So the idea is, if you give me any symmetric lax monoidal functor from the category of finite sets with disjoint union to the category of sets with Cartesian product, we could do this type of thing. I'll define a decorated cospan to be a cospan of finite sets, so just three sets A, B, and N, and two maps I and O, together with an element D of f of n, which we will call the decoration. So the idea is, in our example, the decoration is a choice of an open graph adorning the set of nodes N. But we could adorn the set N with all sorts of other kinds of extra structure, depending on what we chose to be our F. So open graphs will be an example of decorated cospans, but in fact, all the other types of open things that I listed will be also examples of decorated cospans, just with different choices of what functor F we decided to use to say what are the allowed set of decorations. So now, yes?
John, can you please be more, maybe with an example, explicit example? What do you mean by decoration? I missed. And
so a decoration just means a decoration just means an element of this set f of n. So now, what does that concretely? Well, it depends completely on what the set f of n is, of course. Cool. And so in my example, the set f of n was the set of isomorphism classes of graphs on n. So in my example, a decoration on n would be one of those things. So like if here was my set n, n1, n2, n3, n4, the decoration would be the arrows that I've drawn, because the arrows there are an isomorphism class of graphs with that set n1, n2, n3, n4 as nodes.
Okay, sorry for this. Thanks.
Yeah, no, it's that. So just like to go back a little bit, I was like, here's like another example. So here my set could be N1, N2, I didn't draw it very well, N3 and N4. And here my decoration is this electrical circuit. So it's something like a graph, but maybe it's not a directed graph this time. And also you'll notice the edges have resistances associated to them as well. So what Brendan did in solving this problem is he made a different choice of F, such that f of n would be the set of all electrical circuit diagrams that you could draw with a given set of nodes. So you get to craft different choices of f to get any one of these examples here, and all the examples you might dream of, any sort of complicated diagram you could do this trick for. So I was just doing the case of graphs as my sort of as my running example. So we just use decoration as just like a generic name for an element of the set f of n, regardless of what the set is. So we get lots of examples of this type of thing. So it turns out that a lot of work has been done on these decorated cospan categories, and this is a sort of modern, updated version of what Brendan Fong originally proved. In fact, this thing I'm writing down here is probably, actually, I should attribute it to Brendan Fong, but we together, me, Kenny Cursor, and Christina Vasilikopoulou has a kind of updated version of this result, of which I'm only telling you a portion. What I'm saying here is that whenever you have any one of these functors f with the nice properties that we impose, then we get a category where the objects are finite sets and the morphisms are these decorated cospans, like open graphs. Well, to be specific, actually, they are isomorphism classes of decorated cospans. So I could have a decorated cospan here, this A, N, and B. You could have this other one, A, N prime, and B, and they might be isomorphic in the following sense. There might be a bijection between my set N and your set N prime, meaning that my labels for the nodes are just different than your labels for the nodes. And I would have my decoration D, you would have your decoration D prime. But the way it works is that this bijection gives you a way to map my decoration over to your decoration. And then we say that our two decorated cospans are isomorphic if that actually maps my decoration over to your decoration. So basically what we're saying here is that it's not exactly right that decorated cospans are the morphisms we're after. We have to wash out the labels of the nodes in this way to not say that the different labelings of nodes don't count as fundamentally different decorated cospans. So I'm going to skip over this for now and maybe come back to it later. So I want to move, maybe I'll do it now. So this is maybe like a local maximum of abstract nonsense. And maybe, I think this may be the global maximum in my talk of abstract nonsense. And then I will move on to the examples of this to show what it's good for. So in addition to trying to build categories of these open systems in the way that I've just described, we also want to get maps between categories of open systems. And so if I have a particular functor f that lets me build a decorated cospan category, say f cosp, and you have one G, then this theorem here gives a procedure for mapping my kind of decorated cospans over to your decorated cospans. So if you're into category theory, you know that the right kind of thing that goes between two functors is called a natural transformation. And so here, what I'm saying basically is that we have the right kind of natural transformation between my f and your G. Then we can use it to map any one of my decorated cospans where the decorations are chosen from my set f of n over to one of your decorated cospans where your decorations are chosen from some other set G of n. So the idea is that this allows us to relate different kinds of decorated cospan categories. And now I'm going to actually show you how we use this. So I want to now take a severe detour into an application here. So there's a field called system dynamics that I believe may have been invented under the name industrial dynamics by someone at MIT named Forrester in the 1950s, who wanted to describe dynamical systems like business models, like how the stocks of different commodities change over time, using diagrams. And he wanted to, he just devised a number of different diagrammatic languages for describing dynamical systems. And these are widely used now in many different fields. One really fascinating thing about this is that because people can understand diagrams who can't necessarily understand differential equations because they don't know calculus or anything, you can engage communities in modeling the problems that the communities face and get their involvement with the help of a trained expert, but where the community members don't need to know any math at all. So this picture here from Peter Hovman is a nice example. There was a problem in rural India about bringing in a new breed of cows, I believe Jersey cows, instead of the cows that they'd been raising traditionally. And they noticed that it caused some difficulties because the cows behave differently. And so some modelers came in and started trying to make a model of the problem. And this picture here, which you can barely see, is the type of diagrammatic model that they were coming up with. And basically what it is a bunch of names of different things like, I don't know, cows, maybe different kinds of diseases of cows, the production of amount of grain being produced, and various things like that, and how different things affect different things. That would be what the arrows are here. And because you don't need to know math to understand this type of picture, it turns out that in this example, you see all these men sitting around making this model, and you can see in the background there a woman. This is a rather patriarchal village, apparently, so women were not like invited to engage in the model building, but she just went over and looked at this picture here, and she noticed that some link was missing. That is, that she just, without any training at all, she noticed that these were like different kind of important entities and the relations between them, and she noticed, hey, there's one missing here, that this affects this. And so she went up and told them that, and they were able to like improve the model based on her remarks. And so there's a whole field now where people will go into communities and solicit their help in designing models in this diagrammatic way. And in particular, there's a community of epidemiologists who use this type of modeling language. And I'm going to talk about one of the type of diagrams called StockFlow diagrams. And Nathaniel Osgood and his student Xiaoyan Li at the University of Saskatchewan are using these type of models. And in particular, they're among the leaders of COVID modeling for the government of Canada. And they make models that the government of Canada uses to predict over the short periods of time how the rate of COVID will increase or decrease. And so here's a simple example of a StockFlow model, StockFlow diagram. Well, I say it's simple, but it's probably already complicated enough that I don't want to describe it in extreme detail, but I'll just point out a few things. So we have these boxes called stocks, which represent, in this case, people of different kinds. You could use cows, but we're thinking about people. So there's some number of susceptible people who aren't infected with the disease. There's some number of people who are called infectives, who are infected with the disease. There's some number of people called recovered. And then there are these flows, these double-edged black arrows, which describe the processes, which represent the processes whereby people in one stock will transition to become in another stock. So for example, there's a process of losing immunity where recovered people can become susceptible again. And the rates of these flows are crucial, and the rates can depend on various variables, which can depend on other variables, which ultimately depend on these stocks. That's what these blue arrows represent. These represent various variables' functional dependence on other variables. So as I'll describe in more detail, there's a systematic procedure to turn these StockFlow diagrams, which need to be annotated with some names of actual functions, describing the functional dependence of some things on other things. I'll just say how this goes in a minute, but there's a procedure to turn StockFlow diagrams into dynamical systems, which is maybe a fancy name for systems of first-order ordinary differential equations. And that's how you use these StockFlow diagrams. You convert these diagrams with the labels by functions into systems of ODE, and then you simulate the ODE. Now, what's new about what we're doing is compositional modeling. So the idea of compositional modeling is that very often you'd like to build a large StockFlow diagram by composing or sticking together a lot of smaller open ones, just like we built an open graph by sticking together two open graphs. And it turns out that when you do this, the dynamical system for the large diagram can be described as a kind of composite of open dynamical systems for the smaller open diagrams. So in fact, we will see that the math that I described earlier is exactly what we need for this. But the interesting thing is that currently most, maybe may say like almost all modeling for stock flow diagrams is not done in a compositional way. Most modeling is used with a piece of software called AnyLogic, and it's a piece of software that lets you draw stock flow diagrams and label them with functions and actually convert them into systems of differential equations and solve those differential equations. And that's how the COVID models in Canada work, and a lot of other models. But the problem is that this software does not allow you to write separately a number of different models and then glue them together to form a larger model. You just get to do one big fat model in one big fat screen. And the reason why this is a problem is because models are complex, and you would prefer to, in fact, to be able to build them a piece at a time. For example, if you're dealing with different cities, or you have somebody who's an expert on hospitals and somebody else is an expert on some other aspect of the community, you'd like them to be able to separately build their models and then later on stick them together. And to see why it's a problem, here is Osgood and Li's model of COVID written out in AnyLogic. This is actually used by the government of Canada. And as you can see, it's almost impossible to see this thing because it's huge, and I've compressed it down to fit on the page, and you can just barely see. There are like lots of these stocks here, lots of flows connecting them, and lots of these pale blue edges here showing how various flows depend on various variables. So in other words, this is unwieldy and too large to deal with all at once. Well, they have to deal with it all at once because they're trying to deal with COVID, but we'd much prefer to work compositionally. And so that's why Nathaniel, Osgood, and Xiaoyan Li decided to team up with us mathematicians to develop a compositional tool. So in fact, we've done it, and I'll describe it. So they have now created software that supports compositional modeling with stock flow diagrams. And Evan Patterson and Sophie Libkind did all the software development, and I just contributed some of the underlying math of the decorated Cospan categories and the particular decorated Cospan categories that we need for this problem. And we meaning they, wrote this software in programming language called Julia, but there's a package called Algebraic Julia that's been developed by James Fairbanks and of other people I've already mentioned, and even more people. It's a package in the language Julia that lets you do high-performance scientific computing with category theoretic constructs. So Julia is a language that's apparently very good for large-scale numerical calculations. It's unlike some programming languages that category theorists love. This is able to like multiply enormous matrices really fast and do all sorts of brute force computation. But what algebraic Julia is a kind of software package written within Julia that knows about things like categories, functors, natural transformations, pre-sheaves, decorated Cospan categories, and so on. And then you can write software using those category theoretic primitives. So that's what we did. And let me describe a little bit of the math. To do this, I'll only talk about a simplified version of stock flow diagrams, not the full-fledged thing, which is a little bit elaborate. So in its simplest form, what's a stock flow diagram? We can think of it as a thing like this. You'll notice the top part of this looks like a graph, namely two sets and two functions between them. And that's because part of what a stock flow diagram is a graph. It's a graph where the nodes are called stocks. Here are these boxes here, for example. This is an example down here. So the stocks are different kinds of entities, like susceptible people, infected people, resistant people, and I'm afraid dead people. And then the edges of your graph we call flows, and so those are these double-edged fat arrows here, and so they are used to describe how entities from one stock can turn into entities of another. So susceptible people can become infected can become resistant, or infected could become dead in this simple example. But then there's an extra aspect, which are these links, which here are drawn in blue. So every link has a source, which is a stock, and a target, which is a flow. So each blue arrow points from a stock to a flow. And you can have multiple blue arrows pointing to the same flow. And what those blue arrows describe is how the flows depend on the stock. So for example, the rate at which susceptible people become infected depends both on the number of susceptible people and on the number of infected people. That's what these two blue arrows are indicating. But to actually get a differential equation out of this, we need to get some specific functional form for example, how the rate of infection depends on the number of susceptible people and the number of infected people. So for each flow, for each F in our set of flows, we want a function from R to the N, for some N, to R. And more precisely, it's a function from R to the set of links whose target is F to R. So in particular, for example, this particular flow here would have attached to it a function from R squared to R, saying how the rate of this flow depends on two numbers, the number of susceptible people and the number of infected people. This particular one here would depend on just one number. This would depend on just one number. So that's a stock flow diagram in a simple version. And now we're going to talk about how we convert them into dynamical systems. So what's a dynamical system? Well, in this particular context, it's just, we will talk about a dynamical system on a finite set N, and it will just be a smooth vector field on R to the N. If you have such a thing, you can write down a first order differential equation which describes how a point in R to the N moves around with time, moving along the vector field. So what the point means here is we will think of N as some set of stocks, and so x of t will be a number for each stock, saying how much of each stock you have as a function of time, and this differential equation will describe how those change. So then there's a systematic procedure, as I mentioned, to convert stock flow diagrams into these dynamical systems. So in particular, this one here that I showed you before will give you this set of differential equations. So here you'll notice, for example, the flow I is going to be labeled with a function called phi sub I, which says how that particular flow is a function of S and of I. I'm abusing notation over here. S, I, R, and D mean the number of people of the various four kinds as a function of time. Whereas over here, they're just like the labels of the four boxes. So this is saying the number of susceptible people decreases over time at a rate equal to phi I of S of I. But those people are getting infected, and so the number of infected people is increasing in the corresponding way. Similarly, the number of infected people will be decreasing as they either become resistant or die. So those are these two negative terms here. And the number of resistant people will be increasing at the same rate, phi sub R of I, and the number of dead people will be increasing at the rate phi sub D of I. So I'm not writing down a complicated general abstract formula for how you turn any stock flow diagram into a set of differential equations. I'm just giving you an example, but I hope that the example illustrates the general procedure and is maybe clearer than some very abstract looking formula that handles every single example, but we have such formulas. So, okay, so now what does this have to do with all the category theory nonsense at the earlier part of the talk? So what we have here are really two decorated Cospan categories and a functor between them. Why? Because for each finite set, there's a set F of n of isomorphism classes of stock flow diagrams with n as their set of stocks. And that we can prove gives you a symmetric Lax-monoidal functor, sending each finite set n to the set of those stock flow diagrams. And so we can hit it with my first theorem, and we can get a category with open stock flow diagrams as morphisms. So here's a picture of that. So here we have an open stock flow diagram. So we have a stock flow diagram here, but we also have a finite set A and a finite set B, both mapping into the set of stocks of our stock flow diagram. And the point of these sets A and B is that these would allow us to glue together open stock flow diagrams to form larger ones. Just like in my example, I glued together some open graphs to form a larger one. So this allows us to build up big, complicated stock flow diagrams by gluing together pieces. Similarly, for dynamical systems, for any finite set n, there's a set G of n with dynamical systems on n as its objects. And we can prove that this gives another lax monoidal functor in the same sort of way. And we get, oh, sorry, I said double category here. This is, I should just say category. This is like where I was not trying to hit you with even more category theory, but I see a little bit of it snuck through because I didn't change all the words. But anyway, you get another symmetric monoidal category of open dynamical systems by the same theorem. And then finally, this systematic procedure I just alluded to and illustrated in an example, turning any stock flow diagram with some set of stocks to a dynamical system on n, actually is a natural transformation. And thus you can use our second theorem to get a functor mapping open stock flow diagrams to open dynamical systems. So all of this is the type of thing that is implemented in the Julia code that my wiser co-authors have written. And so by doing this, they created a software package called StockFlow, which you can get a hold of on GitHub. And so what it lets you do is it lets you create open stock flow diagrams, that is, build them up, you can compose them to form larger ones, and it lets you convert these open stock flow diagrams into open dynamical systems. And then finally, it lets you solve the differential equations given by these dynamical systems. If you give initial data, you have to give initial values for each stock. And it lets you do a lot of other things. For example, it lets you not only compose decorated cospans, but also what you call multi-cospans. So like here we have three different stock flow diagrams, but in my open stock flow diagrams that I illustrated before, I had functions from two different finite sets into them, but here we allow like functions from multiple finite sets into them. So we have more flexible patterns of gluing together these stock flow diagrams to form larger ones. So basically what we're doing here is we're saying, I know that the type of people that are called E here in this model are the same as the ones in this model and the same as the one in this model. And so I would like to glue all these models together. And so we'll identify this orange box with this one and this one. Similarly, we want to glue this I onto this I, and we want to glue this R here onto this R, and this S here onto this S. And so we can take these three very small models and glue them together and form a bigger model. And that's what's going on in this picture here. So on top, we have what we saw in the last slide. At the bottom here, we've glued together those three different models into one larger model. So the software lets you do that sort of thing. You may notice that I haven't talked about geometry or topology. I warned the people who invited me that would be the case, but topologists like such things as operads, and so this is the closest I'll get to topology. So it turns out that there's a general theory of gluing things together called the theory of operads, and in particular, every decorated cospan category gives you what's called an algebra of a particular operad, called the operad of undirected wiring diagrams. So this is an operad where the operations look like this. So these empty boxes here, you could think of as like, for example, being StockFlow models that you are then planning to glue together in some pattern. And so these black little loose edges dangling out of them are the points which you're going to attach, identify things. For example, maybe identify this and this. So there's a theory of this particular operad, a very important operad that was invented, I guess, originally by David Spivak. And it turns out that every decorated Cospan category gives you an algebra of that, and that is also implemented in Algebraic Julia. If you want to understand what I'm talking about here more clearly, you should read Sophie Libkind's paper about this, called An Algebra of Resource Sharing Machines. He really brought in the use of operads into the decorated Cospan categories and their applications. So some other developments, I'll just sort of sketch where things go from here, so to speak. So Nathaniel Osgood has recently made a graphical user interface for this program StockFlow. So the idea is, of course, that we don't want the people building these models to need to know anything about operads or decorated Cospan categories, or even how to program in Julia. We would like a completely graphical way of building StockFlow diagrams. And so that's what this graphical user interface does. So back behind the scenes is the algebraic Julia program called StockFlow. But what you do as a user is you just fire up your browser, you go to a specific website, and then you can start building StockFlow diagrams just by clicking on things to create these boxes for stocks and these edges for flows, and then like gluing them together. And then you can initialize with initial values and then press run, and it will run and it will solve the differential equations. But the reason why it's so important that it runs in a web browser is that it allows different people to use it collaboratively. So it's not just that one person is able to use this at a time. A team of people will be able to use this and collaboratively build models. And that's like a key aspect of this whole philosophy of modeling. It's still at a primitive level. So at some point I will give talks where I like demonstrate it. But right now I have a feeling that if I demonstrated, I would screw up. And so I don't think I'll try to do that right now, but someday soon. And I just want to mention that there's a lot of other software in algebraic Julia that uses decorated Cospans. So there's something called Algebraic Petri, which implements these open Petri nets with rates, which are equivalent to what are called chemical reaction networks. So they're useful in chemistry, but that's also been applied to epidemiology. There's some software that Sophie Libkind was primarily involved in called Algebraic Dynamics, which implements open dynamical systems. There's something that implements graph rewriting for open graphs. There's some piece of software, the funny name Decapodes, that allows the simulation of multi-physics systems, those meaning physical systems where you have different types of physical models, like one kind of PDE for fluid flow, another kind of PDE for heat diffusion, and so on. It's all using discrete differential forms on simplicial sets to actually do to actually convert these PDE into systems of ODE that you can actually solve on a computer. And you can glue together different chunks of physical systems using the decorated Cospan math. So all of this is open source software, and if you get my slides and you click on these blue things, you can get to the software, or sometimes also papers about it. And so we're building up basically a large repertoire of different simulation methods, all in the same category theoretic framework. And again, I'm saying we because I'm so proud to be involved in it, but the people who are writing the code don't include me. So I'm more on the theoretical end of things. And if you're interested in the theoretical end of things, I recommend these papers. So this first paper here, Compositional Modeling with Stock and Flow Diagrams, describes the particular application that I was mainly talking about today, the epidemiology modeling using stock and flow diagrams. But there's an earlier paper by closely related but different team of authors called An Algebraic Framework for Structured Epidemic Modeling, and they were using open Petri nets with rates to do epidemic modeling. And then if you're interested more in the hardcore math of decorated cospans, like the category theory aspects, I recommend this paper with Kenny Cursor and Christina Vasilikopoulou called Structured versus Decorated Cospans. Partially why I recommend it is that it has references and summaries of all previous papers on these topics, so that it's like a good starting point in some sense that it will lead you to other earlier papers on the topic. So I think I'll stop there, and so I hope I've given you some little taste of how we can go all the way from category theory over to the practical problems of collaboratively building models for epidemiology and other kinds of dynamical systems. So thanks.
Thank you. Thank you very much, John. Very interesting talk on a topic that clearly has many possible interpretations, so to speak, or applications. I have a curiosity, and is very basic. I'm sorry to be so naive. I understand the fact that you need these edges to be directed, and the whole thing makes sense, of course. But there are cases where you might have an immediate back reaction from a nodal point backwards, so in the opposite direction. Or you can interpret this as a lack of an edge, as a superposition of two oppositely oriented edges. I hate to go for more difficult things. I like simple things, as many mathematicians do, but I wonder if you have a comment on this.
I'd say that the framework of decorated cospans is extremely flexible, so it can handle a lot of things. So as I'm sure you know, when someone starts talking about graphs, you typically have to ask them what kind of graph they're talking about. And so graph theorists, professional graph theorists, typically when they say graph, they mean a simple graph where the edges don't have directions, and we are only allowed at most one edge between nodes, and you're not allowed edges from a node to itself. But for each of those decisions I've just listed, you get a binary choice of whether you allow it or not. So there are at least 2 to the 4th kinds of graphs that people are interested in. And so the good news is that you can build decorated cospan categories with any one of those kind of graphs. And you're right that for different types of applications, you may want to use different ones and consider various other variations. So basically, if you sat down with me and told me like exactly what you wanted to do, I could try to dream up a decorated cospan category that would do it for you.
Thank you. There are questions from those attending the talk live? Okay. If no questions, then I thank you, John, again for this beautiful talk. Thank you. Thank you very much.
Sure. Great. Thanks a lot. Pleasure this.